that completes the summary of the fundamental ideas. We will move on to a summary of three different propulsion systems that were discussed in the course: the solid propulsion system, the liquid propellant propulsion system, and air breathing propulsion systems, which in the analysis of which we used the ideas, the fundamental ideas that were discussed and summarized till now. Okay. Let us move on to a summary of basics of solid propulsion systems. Here again I will try to use as much of pictures as I can. What I have shown here is a basic layout of a solid rocket motor. Okay. These equations, as you may recall, are what are used to calculate the equilibrium state, okay, of the solid rocket motor. Or the equilibrium pressure of the solid rocket motor. Whether that equilibrium is a stable equilibrium or an unstable equilibrium is a much more difficult problem to solve, which is also something that we discussed in some detail, and one particular aspect of an unstable equilibrium is the DC shift. Okay. This is another thing that we discussed in the course, and another aspect of solid propellant combustion which we discussed in some detail is predicting the burn rate of composite solid propellants. Okay. Because what is required for this I will explain in the next slide in some detail. What I want to emphasize here is the key idea which was used for the prediction of the composite solid propellant burn rate is the idea of lateral diffusion distance. This d0 that appears here is exactly the lateral diffusion distance, and the ratio of the AP particle size to the lateral diffusion distance is a measure that was used to decide what is the extent to which reaction rate controls the deflagration rate of a solid rocket propellant. Okay. Let us go into some details. This is a basic layout of a solid rocket. Okay. Once ignited using a pyrogen igniter in this case, the propellant starts burning normal to itself along the local normal, and the solid propellant will get converted into hot gases at very high temperatures, typically about 3000 kelvins. Those high pressure high temperature gases expand through the nozzle producing thrust. This is the basic operation of a solid rocket motor, and the pressure inside the rocket motor is governed by a simple balance of how much mass is generated by the conversion of the solid propellant to the gaseous propellant and how much mass goes out. Okay. So, the rate of change of mass which I have expanded here, which is the rate of change of mass is equal to the rate at which the solid propellant gasifies, which is rho p r dot a b, minus the outflow through the nozzle. Okay. P c A T by C star. Recall that the C star is a thermodynamic property of the propellant. This comes from thermodynamics. Okay. And R dot, which is empirically determined usually, has two components. One is called the intrinsic burn rate of the propellant and other is the erosive burning component. There is the erosive burning component. This R dot 0 is usually power law function of pressure. Okay. And in the simple case where let us for a moment ignore the erosive burning component, the equilibrium pressure of a rocket will be simply governed by the balance of the incoming mass with the outgoing mass. C star and rho p R dot goes as P c raised to n, A b is is PCAT by C star, and from here we can simply get the equilibrium pressure to be AB by AT rho P A C star raised to power 1 over 1 minus n. I think in the equation that I wrote in the lecture I made a small mistake, the A C star appeared in the denominator in this equation, but this is the correct expression for the equilibrium pressure, okay. And ignoring the erosive burning component, this will be the equilibrium pressure inside the rocket chamber, and as the burning surface evolves the burning area will change, okay, and the pressure inside the chamber will also change. R dot 0 is typically obtained from experiments, but it takes a lot of trial and errors. Given for a given mission there is a particular requirement of thrust which translates into a particular requirement of pressure as to how the equilibrium pressure should change with time, and that determines what should be the burn rate of the propellant as a function of pressure. And it is not a simple task to actually design a propellant such that it gives the required burn rate, pressure variation, and therefore creating a model, okay, with which a designer can design propellants without having to go through a trial and error process is a challenging task, and the heterogeneous quasi 1D model solves this problem. The heterogeneous quasi 1D model results in a theoretical framework with which R dot 0 can be calculated as a function of pressure without having to do a lot of trials, okay. With this background let us quickly go to the erosive burning, the idea of erosive burning. This was discussed in some detail in the as a part of the course. The key idea is that when expressed, okay, eta, which is the burn rate because including the effect of erosive burning divided by the intrinsic burn rate, okay, when expressed in non-dimensional form as a function of the non-dimensional port flux, port mass flux and the Reynolds number, okay, irrespective of the type of the propellant, irrespective of whether a particular composition is composite or double base, okay, all data when expressed as eta versus G, which is the non-dimensional port mass flux, follows more or less, falls within a very narrow band. That is what is shown here. This is data from several sources for different kinds of propellants using different kinds of ingredients, and irrespective of all these variations when expressed as eta versus G, all data falls within a very narrow band, and this equation is a good fit for this behavior, okay. For some reason I am not able to draw the box, so this equation is a good fit for this variation. What is the conclusion? The conclusion is very simple. Erosive burning is a fluid dynamic effect, okay, because the only variables that appear on the right hand side of the function are the port mass flux or the non-dimensional port mass flux and the Reynolds number. There is no variable that is a function of the composition of the propellant or the burn rate of the propellant, okay. Therefore, while the intrinsic burn rate, which is R dot 0, is a strong function of the composition and many other factors and dependent on the particle size of AP and ingredients, very specific ingredients that are used for making propellants, erosive burning is independent of all those effects. All those composition effects are absorbed into R dot 0. Erosive burning is only a fluid dynamic effect, and that is the main conclusion from this theory, okay. This is called the universal erosive burning model, and the conclusion is that erosive burning is a fluid dynamic phenomena. So now we have seen, recall that R dot is R dot 0 plus R dot erosive. We saw that R dot erosive is a fluid dynamic effect only R dot 0 is composition dependent, and in the case of AP HTPV propellants, HTPV propellants, it is a strong function of the size of AP or the size distribution of AP particle size distribution. DAP is AP particle size, and in a typical propellant can contain particles of, in a typical composite solid propellant there can be AP of different mean sizes. For example, one case that is shown here has 4 mean sizes: 200, 90, 50 and 20, 20, 50, 90 and 200. Not just that, around each mean size there will be a distribution. Okay. Mass fraction of it. Around each size there will be a distribution of particle sizes. Therefore, a typical composite solid propellant having AP as an oxidizer, ammonium perchlorate as an oxidizer, a cross section of it will look like this, as I have shown here: large AP particles surrounded by very small AP particles, and here and there some medium sized AP particles. Okay. So, a cross section is highly heterogeneous, containing particles of different sizes, and the burn rate R dot 0 is a strong function of this distribution. And how do we calculate at what rate this propellant will burn when it has particles of different sizes? So, the simple idea that was introduced is that the burn rate is nothing but the average burn rate of a large number of random lines drawn through a cross section like this. Okay. So, the burn rate of a propellant is simply the length divided by the time, the average time that it would take for such a statistical particle path to burn, and that time is the sum of the time of particles of different sizes. So, the time for the line to burn, the average line to burn, is the sum of the times for individual particles, which is the length of the individual particle divided by the burn rate of the individual particle, and therefore the burn rate of the propellant is Li over R dot I sum inverse. We can arbitrarily take L to be unit length. Okay. So, this is the simple idea that is used to calculate the burn rate of a propellant containing AP particle sizes, different AP particle sizes, and now the question comes: what controls the burn rate of a particle of size DAP? Okay. And this is where the idea of lateral diffusion comes into picture. So, we have a particle of size DAP covered by fuel, and therefore, when you look at it in the cross section, there is fuel, AP and fuel. Oxidizer is issuing from the center, fuel vapors are coming off from the periphery. Okay. So, the question is what controls the structure of the flame and therefore the heat flux that goes to the surface, which in turn controls the regression rate. The idea is very simple. The flame structure will be controlled by mixing if DAP is much larger than the diffusion distance, okay, and the behavior will be close to premixed if DAP is much smaller than the diffusion distance, and that simple idea is what was used to define this non-dimensional variable, which is nothing but the ratio of the AP particle size to the lateral diffusion distance. If you go back and check the equation for D0 is exactly this, okay, reaction controlled diffusion distance. Okay. This simple idea was encoded into this to calculate the burn rate of different particles that constitute the statistical particle path, and from that the burn rate of the propellant can be calculated. Okay. This is the crux of the heterogeneous quasi 1D model. Okay. Moving on to the problem of stability. Okay. So far we have concerned ourselves with calculating the equilibrium state of the rocket, but we have not asked the question whether that equilibrium is stable or unstable. As it turns out, the equilibrium pressure and the equilibrium pressure variation with time that we calculate using the classical ideas, okay, are stable for very short rockets L less than 0.5 meters and for very long rockets L greater than 10 meters. Okay. And as it turns out, this is because the fundamental longitudinal mode frequency for a very long rocket motor is very low, it is only 25 hertz, and for a very short rocket is very high, about 1000 hertz. It is only intermediate sized rockets which are a few meters long, 1 to 3 meters or something like that. The frequency is about 250 hertz and the composite solid propellant responds to perturbations which are around 250 hertz. If you have very short motors, your frequencies are very high, you are far to the right, your response function is lower and therefore there is no instability. If you go to towards the left, which is very long motors, the fundamental frequencies are very low, again the response function is very small and therefore there is no instability. But tactical solid rocket motors are sort of in the instability sweet spot where the frequency and the response, the peak response and the frequency matches. So what are the consequences of this? The consequence is that the instability will cause a growth of small perturbations like this, and what is unique to solid rocket motors is what is called DC shift, is a shift in the mean, okay, is a shift in the mean pressure and very large amplitude oscillations around this mean. This is a characteristic of solid rocket motors, and we saw that during the DC shift the propellant is subjected to very high depressurization and cyclic depressurization and pressurization phenomena that causes cyclic extinction and dramatic reignition, where the burn rates can go to 10 times the mean value before it comes to the mean position, quenches again because of high depressurization rates, remains quenched and ignites dramatically and comes back. Okay. This is the origin of DC shift was conclusively shown using CFD calculations, okay, where linear growth or exponential growth of oscillations when a critical amplitude is crossed, where the depressurization rates have crossed the critical value, the propellant undergoes extinction reignition cycles leading to DC shift. Okay. And a simple scaling for the critical depressurization rate is that the time scale for depressurization 1 by P0, you start from a pressure of P0, okay. The inverse of this is the time scale for depressurization. If this becomes comparable or smaller than the conduction time scale, which is alpha over r dot 0 squared, okay, then the propellant will extinguish. This will lead to quenching. If the propellant does not have enough time to adjust to the changes in the gas phase temperature profile, it will quench. Okay. And in the case of cyclic depressurization pressurization, there is dramatic reignition, because when the propellant quenches, the solid phase still remains at a higher temperature, it remains in the cooked state, and when pressurization happens, establishment of the gas phase flame will simply gasify this entire mass of cooked propellant in one shot, leading to very high burn rates, and that is the origin of the DC shift in solid rocket motors. Okay. So that completes the discussion of well, one point that I missed is what causes increase in the amplitude of what causes the growth in the amplitude of small perturbations, called the linear instability. This is because of the heterogeneity in surface enthalpy. Okay. To put it in simple terms, it is the binder melt fluctuation, okay. You have AP surface surrounded by binder, and instability is usually associated with the use of burn rate inhibiting additives, and these inhibitors, because they are added to the binder, they inhibit the gasification of the binder, leading to overflow of the melted binder over AP, causing the burn rate to go down. This is what happens when under steady pressure conditions, but when the pressure oscillates, the same binder melt can actually fluctuate, leading to a very large fluctuation in the burn rate, which when coupled to the pressure fluctuations or the acoustic fluctuations in the rocket motor can lead to growth of oscillations, and when the oscillation amplitude crosses a critical value, this leads to DC shift. Okay. That is the complete picture of instability in solid rocket motor.